Now, today we will go on the Z transform, okay? Actually, the inverse Z transform. By the way, let me introduce myself. My name is Tansu Filik, and we can make a overview. So, for continuous time signals, in order to analyze these signals and systems, an important tool is Fourier Transform. So the continuous time Fourier Transform is actually, you have a continuous signal and you change domain, and this domain is frequency domain, omega. Okay. This is just for remembering. So you take xt e to the minus j omega t dt. Okay. So in order to find systems or signals Fourier transform, this integral should converge a finite value. Let's say if this xt is an unstable system, let's say ht or something like this, a linear time varying system which is unstable, in this case this integral will not converge, it will diverge, and the Fourier transform is in this case is not defined. Okay. So for this, another tool or another analysis tool is Laplace transform. So it is Laplace transform for continuous time signals and systems is important for us. If you have an unstable system and if you want to analyze this system, you need a new tool, and this tool is Laplace transform. It is simply like this, the definition of this. So what is the difference? In this case, instead of j omega, you define an s parameter, and this s is something like this. It's sigma times j omega. Okay. So there is a real part and also the same part for the Fourier transform. So by defining this parameter, you can analyze the unstable systems, and you can tell that, okay, when this integral is, let's say, unbounded, when it diverges, by changing these parameters, you can find or you can analyze systems, unstable systems, with this mathematical tool. So this is the Laplace transform. This is the Fourier transform. So these are for continuous time signals and systems. What about discrete time systems? In this case, you're going to sample, let's say this is the sampling period. With sample period t, okay? So this is, in this case, a digitized version. So it is a discrete signal or a discrete system in this case. So for this, there is a discrete time Fourier transform. Okay. What is the definition of discrete time Fourier transform? It is simply x e to the j omega. What? So since this is a discrete system or a signal, okay. So this is the discrete time Fourier transform. Again, same problem is valid in here. Since this signal or system is unbounded or unstable, in this case, this infinite summation will diverge. Okay. So for the discrete time systems, we need a tool in order to analyze unstable systems or unbounded signals. Okay, so this is the Z transform. What is the definition of Z transform? I think last week you have seen this. Let's remember. So again, this is a summation from minus infinity to plus infinity, xn z to the minus n. So it is actually the discrete counterparts of this Laplace transform. So the z is in this case is r times e to the j omega. So this is the definition of z. So what about the absolute of z or magnitude of z? It is equal to r. And this one is the same with the discrete Fourier transform. So this is a rotation, or this is related with Fourier transform. So you define a parameter r for in order to analyze unstable systems or signals. Now this week we will start with inverse Z transform. This is a very important tool, Z transform, for analyzing the discrete time signals and systems. And how can you find the inverse Z transform of the signals? So the definition, in order to find the definition, let's write the Fourier Z transform, definition of Z transform again. As you know, Z is equal to R times e to the j omega. So x, let's put r e to the j omega instead of z. So xn times r to the minus n e to the minus j omega n. So we know the definition of the discrete Fourier transform. It is in here. And as you see, what is this? This one, e to the minus j omega n, is this part, and this is the xn. So it is the Fourier transform of this. So it is e to the j omega. So in this case, we put an r to the minus n multiply with xn. So this is the Fourier transform of, actually this expression is the Fourier transform of what? Xn times r to the minus n. So you put a decaying, or I don't know, it is depends on r, an increasing function, multiply this with the discrete sequence, okay? So you take the Fourier transform and you find the Z transform in this case. So this is the relation between Z and discrete Fourier transform. Okay, let's write this expression again. R times e to the j omega is equal to Fourier transform of xn times, r minus n. Okay, you find this expression. Okay, how are we going to turn the inverse Fourier transform? Let's continue from here. So apply inverse Fourier transform to both sides, as you see. So the inverse Fourier transform, it is something like this. Inverse Fourier transform of x e to the j omega. Sorry, there is an r in here. And inverse Fourier transform of the right side. So it is Fourier transform of xn times r to the minus n. So inverse Fourier transform is directly is equal to xn times r to the minus n. Okay. So you can take xn from here because we are trying to find the definition of the inverse Fourier transform. Okay. So we're going to find xn is equal to blah blah. So take xn in here to this side. and it is equal to what? R to the n. So you put this term into left side, and inverse Fourier transform of x r times e to the j omega. So the problem is find the inverse Fourier transform of this expression. Okay. So xn is equal to Rn times. So we know the definition of inverse Fourier transform. Let's remember it. The inverse discrete time Fourier transform is equal to 1 over 2 pi. So it is 2 pi symmetric. X e to the j omega and e to the j omega and d omega. Okay. So this is the definition of inverse Fourier transform. Okay, what about the inverse Fourier transform of this in this case? It is 1 over 2 pi. Integrates from minus pi to pi or 0 to 2 pi. X r e to the j omega. The only difference is this r, okay. E to the j omega and d omega, okay. So actually this is the inverse Fourier transform, inverse Z transform now. Let's do some manipulations in this equation. So we can put this exponential factor inside the integral. So the equation is in this case 1 over 2 pi x r e to the j omega. You put this term into here, and it is the power of n. There's a power of n in here, so it is simply r times e to the j omega over n, okay, d omega. Okay. So the remembering part is okay, so we can erase this. So as you see, there is an r term in here, and the remaining is similar. So when r is fixed and omega varying over a 2 pi interval, when r fixed, you can fix r into a finite value, and varying omega over a 2 pi interval. Now we can change the variables in omega. Let's change variables omega to z. So we know the definitions, and we can do this. What about z is equal to r times e to the j omega. It is given by definition, as you see in here. So, and you know r is fixed. What about DOZ? In integrate, you're going to find d omega in order to change the variable. So it is j times, you're taking the derivative of this right side, r e to the j omega, d omega, okay? So this is what? Since this is dz, it is j times, so this is z, you know, z times d omega. Good. What about d omega in this case? D omega is 1 over jz and dz. So simply 1 over j z to the minus 1 doz. The integration is, as you see, it is over a 2 pi interval in omega, so it is bounded in this case. So in terms of z, let's think it in the variable z. So it corresponds to one transversal around the circle. So what do you mean with this? So if you change the variable, in this case the xn is equal to this equation. 1 over 2 pi is still in here. There is a j term. It comes from here. And there is an integration. And in this integration is as we said that for z variable, it's a transversal around a circle. So we put this symbol in order to show this. So it is x of z in this case because this is z. Okay, x of z, and this one is z to the n, and 1 minus is coming from here. This is z to the n, and the other one is z to the minus 1, b of z, yeah? So if we erase this term, and we can directly write this. So this is the definition of, or expression of, the inverse Z transform. So this symbol denotes the integration around a counterclockwise, okay, closed circular contour centered at the origin. It means something like this. So this is the real part, this is the imaginary part, and if you fix R, whatever, this is the counterclockwise, this is the angle, omega 0, let's say. So it means that from 0 to 2 pi, a full circle in this case, okay? So this defines this. So this is the formal expression for the inverse Z transform, okay? Formal expression. Of inverse Z transform. So now we are going to find the inverse Z transform of some sequences, but this definition is not so useful, and so you avoid using this definition, okay? So how can we find inverse Z transform in this case? But you should know the formal definition, okay? Okay, we have finished here. Let's do an example. So you're given x of z. It is something like this. Numerator and the denominator terms. As you know, if you have a xz, if you say have a signal or system in z domain, also the region of convergence should be indicated in this case, okay? So for this example, the absolute of z is defined in this case. So this is the region of convergence. So you can maybe plot the region of convergence. You already learned this. So there is 2 poles. One is at 1/4 and the other one is 1/3. So in this case, let's say this is the z plane. This is real. This is the imaginary axis, and this is 1/4 and this is 1/3. Let's say, okay. These are the poles. So for this definition, the region of convergence is a ring, okay? So let's find the inverse Fourier transform of this expression. How can we do this? You can factorize this expression into two parts. It is 1 over 1 minus 1 over 4 z to the minus 1 plus 2 over 1 minus 1 over 3 z to the minus 1. Okay? You can write this expression into this form. So, what about for this sequence? From the previous course, this, as you see, it is greater than, absolute z is greater than 1 over 4. So this is a right-sided sequence. So z is greater than 1 over 4. Okay. So what is the inverse Fourier transform of this expression in this case? It is equal to u to the n. Yeah. This is right-sided, so you can call this x1 n, the inverse Fourier transform of this, only this part. So what about this part? So in this case, there is a pole in 1 over 4, and your region of convergence tells that the absolute z is less than 1 over 3. So this part is left-sided, okay? So how can you find the inverse Fourier transform of this part? So this is 1 over 3. So in this case, this is, let's say, x2n. It is minus 2 times. A minus term will come, since this is a left-sided sequence. 1 over 3 n u minus n minus 1. So what is the inverse Fourier transform of this expression? It is the summation of x1n plus x2n. So if you have such an expression, you can divide this into two first-order systems or signals, whatever, and then you can take the inverse Fourier transforms and add these and find the final inverse Fourier transform in this case. So it is possible. Also, let's say this is the z transform. Someone says that let's z is equal to 1 over 3. So in this case, what is the region of convergence? Or how can you plot the region of convergence for this example? This is for exercise for you. Exercises for you. Let's say z, the absolute z is greater than 1 over 2, 1 over 3, sorry. So in this case, this is the region of convergence for this specification. And then if you find the xn, you will see that it is different than this expression. So another possibility for this is maybe the z is less than 1 over 4. So in this case, the region of convergence is in this part. So there are some possibilities for these. There are three possibilities in this case for these expression. And for all these possibilities, there are different inverse z transforms. So the region of convergence is very important and very critical for you. So if you have an expression something like this, oh, tell me what is the region of convergence in order to find the inverse Fourier transform. You should know this, okay? So there are three possibilities. One of them is this. The inverse Fourier transform is calculated in here. The other possibility is this, and the third one is this. So the exercise for you is that find the inverse Fourier transforms when the region of convergence is this or this, okay? You can do this yourself. Now we will go on some examples, some important examples. So in your final exam, you will have some questions from inverse Z transforms. So be careful about. If someone give you a x of z expression is something like this: for z square times 2 plus 2z to the minus 1. And what about the region of convergence? The magnitude of z is greater than 0 and less than infinity. Okay? So, as you see, this is the whole z plane, okay? Except the origin and infinity. So, how can you find the inverse z transform of this expression? It seems very simple. There is no numerator term in this case. Let's remember the Fourier z transform expression. It is what? From minus infinity to infinity, xn times z to the minus n. Okay? So this is actually the expression that you are looking for inverse z transform. As you see, the xn terms is multiplied with this z minus n. So in this case, it is simple to find the time sequence for this z transform. How? For n is equal to 2 and 2 for n is equal to 0, because since n is equal to 0, this expression will be 1 and n times 1. For what? For n is equal to 0. If n is equal to 0, x0 times 1. So this is 1. What about the other expression? So I'm sorry, this is minus 2. This term, if n is equal to 1, this is z to the minus 1, and 3 times z to the minus 1. So this is xn 1 in this case. N is equal to 1, so it is 3, this term, okay? For the other n's, as the value of xn is 0. So let's say 4 times z to the 2, if you put minus 2 in here, z to the 2 is equal to x2. So what is the, in this case, inverse z transform of this expression? xn. It is simply 4 times delta function, delta n plus 2, n times 2 delta n, this is for 0, x0, and 3 times delta n minus 1. So it is very simple. In this case, what about x minus 2? Okay, x minus 2 is 4. What about x0? x0 is 2. And what about 1? x1 is simply the 3. All the other values for xn is 0 in this case. So this is the inverse z transform of this expression. Okay, so it is very simple. 4 delta n plus 2. What is the general expression? So in general, n plus n0 is your time sequence. If you take the z transform of this, it is z to the n0. Okay, another simple example for this. Let's say 2 plus 3 z to the minus 5. What is the inverse Fourier transform or inverse z transform of this sequence? What about xn? xn 2 delta n, right? And 3 times delta what? N plus 5. n plus 5, okay? Sorry. N plus. Oh, I'm sorry. I'm sorry. This is minus. I think that it was plus. So when I write, I put a minus in here. So it is n minus 5, okay? Now, this is a simple example for this. Let's go on. So as you see, having z or z minus 1 terms, let's say that having z or z minus 1 polynomials is the best way to obtain inverse z transform. Okay, as you see, this is a polynomial and it is a second order polynomial for z square and the other terms. So if you have a polynomial in this form, the inverse Fourier transform is very simple. As you see, it is easy to find the inverse Fourier transform. So having this z or z minus 1 polynomial, okay, this is a good situation for you. If you have a polynomial in this form, you can directly find the inverse Fourier inverse z transform. Okay. So let's do an example. Now the z transform is 1 over 1 e to the z minus 1, and the region of convergence is greater than a. So it is a right-sided sequence. So how can we find the inverse z transform of this sequence? With this way. So you should find the polynomial of this expression. Okay. So you can make a division in this case. Since absolute of z is greater than a, so this is the order of your polynomial. This is higher order, and this is minus 1. So in this case, it is 1 minus e to the a times z to the minus 1. You can make this division. Okay. Let's try to make this division. So it will give you a infinite polynomial. Okay. Multiply with 1. So what? It is 1 times e to the z minus 1. Subtraction. 1's will cancel. So e to the z minus 1. Okay. Okay. Let's multiply or write e times z to the minus 1, a times z to the minus 1. If you multiply this with this term, it is equal to what? A to the z minus 1 minus a square z to the minus 2. And subtract this expression. These terms will cancel, and it is a square z to the minus 2 in this case. So plus, you're going a square z to the minus 2. Multiply with this. It is a square z to the minus 2 minus a cube z to the minus 3. Subtraction, cancel these terms, and again it will go like this by increasing the powers. Okay. So as you see, this division will give you an infinite long polynomial, but the shape of polynomial is now, I think, clear. Z to the minus 3, and this will go something like this. These powers will increasing after each division. So what is x in this case? 0. x0 is 1. So this is the infinite length polynomial, as you see. x0 is this. What about x1? It is z to the minus 1 term, so it is a. What about x2? it is a square in this case. What about x3? It is a cube, and it goes something like this. What about xn? Xn is equal to a to the n, but it tells us that this is a right-sided sequence, and it starts from 0 and goes 1, 2, 3, 4, 5, something like this. So for the left-sided sequence, for -1, x -1, there is no value, okay, because it is stated in here. So put a un term into here. So as you see, this is the inverse Fourier transform of this expression. You do this by simply dividing these two terms, okay? Okay, let's change the region of convergence for this expression. Someone tells that this z is less than absolute a. So in this case, let's say this is the region of convergence and this is the a. In this case, the region of convergence is here. So this is a left-sided sequence in this case. So for this example, you should do this division according to your polynomial order, because this time this term is higher order than 1. So you put this and make this division with this expression in this case. So it is a minus 1 z. If you multiply these two, this term will be 1, because the minus terms will cancel and the powers are reverse order, minus a minus 1 times z. So if you do the subtraction, in this case, ones will cancel and it is a minus 1 z. So in here, it is, in order to get this expression, a minus 2 z2. This is z1, simply. So it is a minus 1 z minus, okay, a minus 2 z2. So this will cancel and it is a minus 2 z over 2. And this term in this case will go a minus 3 z3 in this way, okay? So since this is a left-sided sequence, what about x minus 1? You know the Fourier transform in this case. If z1, it is zn minus 1. So x minus 1 is in this case what? Minus a minus 1. What about x minus 2? It is simply the a minus 2. And it goes something like this. Finally, what about the xn? It is there is a minus sign in here, and u to the minus n minus 1. Since this is a left-sided sequence and it starts from minus 1, it starts from minus 1 and goes through minus infinity. The other values, the right side is 0 in this case. So this is the inverse Fourier transform of this expression. So you find this expression simply dividing these polynomials, or numerator over denominator. Okay, another example. So as you see, this is a bit complicated expression. So how can we find the inverse Fourier transform of this expression? It is not so easy. We can you write the polynomials in this case? So it is possible, because since the region of convergence is this, and since this is right hand sided, so e to the a z minus 1, absolute of a is minus 1, or magnitude of this term is less than 1. So in this case you can find the power series expansion of this logarithm term. Okay. So in this case we can do power series, Taylor power series expansion of this logarithm term. So one maybe give this expression to you. So you should not you do not need to know this the expansion of this term. You can look from a table or from another source. So for 1 plus v, what about Taylor series expansion of this logarithm? It is simply from 1 to infinity so this expression is given to you. Okay, you know this expression. This is an infinite summation, as you see. So how can sorry, for v less than 1. So how can you find the inverse Z transform of this expression by using this Taylor power series expansion? Let's remember, what about the Z transform? It is an infinite summation, as you remember, xn times z to the minus n. Okay, so this is the definition of Z transform. Okay, please check these two expressions in this case. So this is the log 1 plus v. It is in this case log 1 plus e to the z minus 1. Okay, so this is the expression. What about, so it starts from 1 through infinity, minus 1 and plus 1. What about v? V is in this case a times z to the minus 1. So it is a to the n, z to the minus n over n. It is same. Okay, so we can write this expression by looking the power series expansion of this term in this form. So now check these two expressions in this case. There is an xn term and there is a z minus n exponential term in here in this case. So in your expansion there is a z minus 1 term in here. So what about this part? Is the inverse Z transform. This part is xn in this case by looking these two expressions. So what about the xn? Xn is simply minus 1 n plus 1 times e to the n over n. For what? Let's say this is absolute v is less than 1, because this expansion is valid only in this condition. So similarly in this case we tell that it starts from 1 and starts from 1 and goes through infinity. So we write in here n is less than greater than or equal to 1. What about n is less than or equal to 0? In this case it is 0. So now this is the inverse Z transform of this expression. So you can only use the power series expansion if it is possible. Arkadaşlar bir ara verelim.